Hi, I'm Erik. I'm from Unicamp, Brazil, and today I'm talking about my work on efficient visual attention with deep learning. The first question we may ask is, what is visual attention? Let me introduce you the concept. We all know how important vision is to complex human beings. The problem with vision is that it's very expensive to process. Some neuroscientists believe that over half our brain is involved in some visual-related task. Furthermore, we are constantly receiving an overwhelming amount of visual information, most of which is totally irrelevant for whatever the task is at the moment. It would be very inefficient and maybe even impossible to process all this information with the same intensity. This problem is solved by our mind with attention. Not only limited to vision, attention functions as a mechanism to guide and focus our cognitive capacities only to the stimuli that is important to a given task at a given moment. Attention simplifies the complexity of the information of the world in order to make it tractable. In more concrete terms, we can define visual attention as the process of selection of specific spatial regions of the visual field for subsequent cognitive processing. In other words, visual attention focuses our vision to a specific region of the scene, which will be analyzed with more intensity than the rest. An useful distinction in the taxonomy of attention is that of top-down and bottom-up. Top-down attention is the component that tends to guide our focus according to our goals. Bottom-up attention, on the other hand, refers to when conspicuous, abrupt stimuli suddenly grab your attention. If you are walking on the street, for example, and there is a car crash in front of you, the sudden loud sound and the abrupt movements of the cars will very likely cause you to immediately and unconsciously guide your attention to the direction of the accident scene. In this work, we focus on the latter, bottom-up attention, which can also be called visual saliency. Let's see some specific examples of how visual saliency is manifested in your vision. At a first glance in this picture, most of you probably looked first at the blue object in the scene. This is because it is the most distinct object of the image regarding color. Color contrast is widely known to cause an object or part of the scene to be visually salient. It is not specific to the colors green and blue. In the example, you probably also looked first at the red object. Another type of contrast that grabs our focus is the size contrast. In this example, the biggest object is more likely to be analyzed first. Orientation contrast also plays a role in visual saliency. In this example, the most salient objects are the ones that tend to be in a horizontal position. The phenomenon is not true only for synthetic images. In real-world examples, there is usually one or a few objects that stand out due to a combination of previously mentioned features and other factors. In this example, the fire extinguisher is the object most likely to be first identified by humans. One way to represent the average salience of regions of an image is by means of saliency maps. A saliency map for a given image is simply a correspondent grayscale image, whereas regions with high saliency contain highly valued pixels. These maps are usually computed with eye fixation data from a reasonable amount of humans that looked at the respective image. In the example, the saliency map on the right for the image on the left suggests that the traffic sign is the most salient region of the image. Multiple regions may be considered to have a high saliency. In this example, the orange creatures seem to be the most salient objects. Faces are usually very salient to humans. This is reasonable given our social nature. The question that arises is, can we make computers generate saliency maps? In other words, given image I, we want to compute the corresponding saliency map S that reflects the visual saliency map of the image according to humans. There have been works on computer-generated saliency maps since more than 10 years ago. The first visual saliency prediction systems relied on handcrafted features inspired by findings in psychology and neuroscience, such as the salient contrasts we mentioned earlier. One notable example of visual saliency systems with handcrafted features is Focus. The image illustrated is the bottom-up component of the system proposed by Frintot. Based on findings we mentioned earlier, the proposed bottom-up method extracts feature maps such as color, luminance, orientation, contrast, and others at different scales. These feature maps are combined to form the final saliency map. The problem of visual saliency models that are based on the extraction of handcrafted features is the same problem as any other such system in computer vision. It is generally expensive and time-consuming to elaborate such features, and they don't necessarily adapt or generalize well to all possible nuances of images. Input images may be as simple as the synthetic image, or as complex and nuanced as another image, for example. As well as a variety of other problems in vision, there has been a shift to deep learning-based models to predict visual saliency. Deep learning architectures, such as convolutional neural networks, offer the advantage of automatic learning of feature maps to extract. Depending on the architecture, learning features can have a hierarchical abstraction level. For example, initial layers might learn to extract low-level features, such as borders. Subsequent layers may specialize in identifying lines, circles, and further abstract concepts, such as whole objects and faces. A variety of works on deep learning applied to visual saliency detection have been proposed, and the current state-of-the-art models are not all deep learning based. A variety of proposed works such as DeepFix, Silicon, MLNet, and others base their architecture on using pre-trained weights from large classification networks such as VGG16, illustrated in the picture. Although mentioned models yield impressive performance, a problem to consider is that they are usually very computationally expensive. As mentioned earlier, most models are based on very large classification architectures. There is the benefit of transfer learning for the task, but on the other hand, the number of parameters in mentioned models range from around 15 million to 25 million. And useful application for saliency detection systems may be, for example, robotics. So a natural question that arises is it possible to obtain a deep learning model for visual saliency detection that is more efficient, yet reasonably effective? A performance cost is very likely to occur, but depending on the application, it may be reasonable to exchange a small hit in performance for a more computationally efficient model. To obtain such efficient model, then our work proposes to elaborate a deep learning model with a completely new architecture specific for visual saliency detection. Removing dependency on classification pre-trained models allows for a new layout that uses less parameters. And 2, data preprocessing specific for the context of visual saliency. As in the case of IDEN 1, not using a model originally trained for other tasks allows for more flexibility regarding the data processing we apply to the input images. We can thus apply processing methods that are known to be useful in the visual saliency context. With these requirements in mind, we propose DeepPic, a convolutional neural network designed specifically for the task of visual saliency prediction. The architecture is composed of mainly convolution and pooling layers that extract features at increasingly higher abstraction levels. Let's examine the network in more detail. There are 4 main blocks in the network. Each block ends up with a downsampling operation to reduce the image dimensions by a factor of 2. Block 1 is the input. The input image has arbitrary width and height and is in LAB color space format. Previous work suggests that the LAB color space is more related to the visual system of humans. A convolution with 48 filters with kernel size 3x3 is applied, followed by the ReLU nonlinearity and maxpool. Block 2 works on feature maps with half the dimensions of original image. 2 3x3 convolution plus ReLU blocks are applied, with more filters to allow for more complex combinations. In the end, another 2x2 maxpool is applied. Block 3 is composed of 4 3x3 convolutions plus ReLU blocks in sequence. Again, the number of filters increase as the abstraction level increases. The dimensionality reduction at the end of each block allows for more filters, with less performance hits. In the end, maxpool is applied. Block 4 has as input feature maps with 1/8 of the original width and height. A sequence of 8 inception layers is applied in sequence. There were previous experiments to determine the number of inception layers to balance performance and efficiency. The inception blocks will be further discussed in the next slide. Finally, The 144 maps are averaged via a 1-by-1 convolution operation. Note that the final map is of dimensions h by 8th and w by 8th, so bicubic interpolation is applied in order to restore the map to the original dimensions. The inception layers used are each component composed of 4 operations applied in parallel and final concatenation. The idea of the inception layer is to apply different types of convolutions that capture different scales of the image. Convolutions of kernels 3x3 and 5x5 are applied, with reduction of numbers of input maps being applied before. These capture large spatial areas of the maps. Also, convolution of 1x1 and max pooling operation of 3x3 are applied. In the end, the result of all these operations is concatenated and passed along. This allows the network at training time to choose from operations of different scales. As previous works such as Vocus show, it is important to consider different scales in the context of visual saliency, and inception models help achieve this. The two main data processing methods used were: one, as mentioned earlier, we use LAB color space. This color space is composed of red-green, yellow-blue, and luminance maps, which are more closely related to the human visual systems. And two, in classification tasks, input images are usually normalized channel-wise by the statistics of the respective channel over the entire dataset. In the context of saliency, it is more interesting to normalize each channel by the statistics of the channel of the image itself. So for each image, each channel, for example A, is normalized by subtracting the mean of the channel A and dividing by the standard deviation of the channel A itself. We train the network from scratch. The Silicon dataset is initially used. This dataset contains 15,000 images collected in a crowdsourcing effort. Images are reflected horizontally randomly. After training with Silicon, we use the JUT dataset, composed of 1,003 images and data from human eye fixations. The objective function to be minimized during training is the correlation coefficient between the predicted map P and the ground truth T map. The correlation coefficient is given by the covariance of P and T divided by the standard deviations of P and T. This metric is reasonably balanced when penalizing the predictions for false positives and false negatives. It also does not force the network to produce values in a specific range. This is not necessary, since the image can simply be normalized between 0 and 1. As mentioned earlier, training was divided in two main steps. First, the network is trained on the Silicon dataset. We use stochastic gradient descent with Nesterov momentum. The learning rate is 0.009 for 5 epochs and 0.001 for 3 epochs. The batch size used is 10. The second training step used only images from the JUT dataset. The learning rate was smaller and we used L2 regularization and smaller batch sizes. This step was run for 2 epochs. Let's now visualize some maps generated from the network. The input image is represented at the top. At the bottom left corner, the ground truth saliency map. At the bottom right corner, the predicted saliency map. This is another example. And another example. The generated images seem reasonable, but a more objective evaluation is needed. MIT maintains a broadly used visual saliency benchmark. One of most widely used benchmarks is the MIT 300. 300 held out images from a variety of scenes and dimensions. We submitted our model to MIT 300 benchmark in order to see how it compares to other models. The table shows the main metrics obtained on the MIT 300 benchmarks. Results on the website are sorted by AUC JUT. We compare these models to the models mentioned earlier. These models, at the moment of the evaluation, scored consistently among the top 10 models across the 8 used metrics. The results suggest that, while having around 1/4 the number of parameters of other models, the proposed model still yields results comparable to the state of the art, and even better than some more complex models. The results suggest that it was possible to obtain a more efficient model, yet with reasonable performance. Some conclusions are: it is possible to obtain more efficient convolutional neural networks for the tasks of visual saliency prediction. Neural network architecture and data processing specific for the context of visual saliency showed to be important. The proposed model yields results comparable to state-of-the-art, while with a parameter reduction of at least 3/4 compared to similar models. Some topics for future work include even more efficient networks, maybe further exploration of more efficient architectures, and studies on works that try to achieve the same goal for other problems can be useful. Salience prediction for video is also a problem to be explored. The main concepts of the work may be applied in order to obtain a real-time model for application in robotics, for example. Acknowledgements. We thank PBIC, CNPq for the support. Well, this is our work. Thank you very much.